Okay, so let's say in Excel, you wanted to calculate the mean or median or standard deviation of any of these values, okay? So let's say you type in a bunch of values, 20, 45, 65, 80, 95, 57, okay? If you want to calculate the mean, okay, are you guys familiar with using formulas and stuff in Excel? I hope. Okay. No? Maybe? Okay. It's been a while. So you tap one of your cells and you hit the equal sign. Okay? And you're going to get the mean, you type in average and you hit parentheses and then you highlight the numbers that you want to enter into your formula. Okay? So notice I have equals average, and it says A1 colon A6. That means start at cell A1, go all the way down to cell A6. Okay, because I've got all of my numbers that I want are in this column right here. Okay, now you can highlight this with your mouse. You can type in A1 colon A6. And average will give you the mean. You hit enter, and it calculates the mean for you. And we can verify this. I'm going to do this one time. You can do 20 plus 45 plus 65 plus 80 plus 95 plus 57, and I divide by 6. And indeed, on my calculator, I get 60.333, and over here, I get 60.333. So that is the mean. Let's say you want the median. Okay, you're going to do the same type of thing, except you type in equals median parentheses. And what do we want? We want A1 through A6. Now you can, again, so this time I typed it, but you can highlight it with your mouse. A1 through A6, same thing, right? I want the same 6 numbers in there. Yeah, A1 colon A6, okay?
So what did you type it first? You said to get the median, you type in what?
The equal sign, okay? So here, so for the mean, what you enter is you click the cell and you type in equals average parentheses and then your range of cells. So in this case, A1 through A6, okay? And for the mean,
you have to close it.
yeah,
Close the parentheses.
you close the parentheses. Okay, now Excel is often smart enough to close the parentheses for you if you don't do it yourself. Okay, but it's sometimes Excel, trying to be smart, will close the wrong parentheses because you can put formula parentheses within parentheses, and sometimes it gets confused and it does the wrong thing if you don't specify the parentheses yourself. So I always say it's good practice, or it's a good method to always type in the parentheses yourself. So that's the median. Okay. You can get the standard deviation. And you type in SD. Oh, I'm sorry, not SD. STDE. And you want standard deviation dot S. Okay, so you can do standard deviation, but you'll notice STDEV. This is what they consider the deprecated formula, which means it still works, but they recommend using .S, .P, okay? Now, we didn't get into the difference between .S and .P. For the standard deviation, STDEV.S, and then you put in your numbers, your range of numbers. Okay, so I'll write that over here, okay? I'm not, okay? It's STDEV.S parentheses A1 through A6, okay? Also, STDEV without the .S also works, but this is what they consider deprecated, okay? So depending, if you have an old version of Excel, you might have to use this one, okay? But this is the new recommended thing, okay? Just like before, they always said put 2 spaces after a period. No longer, right? You only do 1 space after a period. So that would be the deprecated method. So that's to find values like the mean, median, standard deviation. I don't think there's one for IQR. There might be interquartile. Yeah, no. So the IQR and the range and the quartiles, those are more difficult to find. So, there aren't designated formulas, but you can do mean, median, and standard deviation. Okay.
So do you have to highlight the A or B or C or D, whatever you want the answer?
So you enter wherever you want the answer, you put that into one of the cells and you hit the equal sign,
Okay.
and then you type in the formula. Okay.
Go back to standard deviation.
STDEV for standard deviation .s. Okay. There is a .p, and it's for a population.
Oh,
Um,
Can you confirm the standard deviation by calculator?
do you know the formula for standard deviation?
Yeah.
Okay, so to calculate it by hand, you have to find the deviations, right? So you do 20 minus 60.33 for each of these. I don't know if this is a good use of our time, to be honest. I promise you, the standard deviation from Excel is correct. Okay? All right. We don't.
I want to know the rate by hand.
You want to do? Okay. Standard deviation by hand is. All right. So this is how you do standard deviation by hand. Okay. Do you want me to do this? Huh?
it's in the book.
You want to do this?
No. I don't want to do that. I just want to know.
I'm not sure if I understand your question. Because you want me to do this by hand on the calculator? Is that what you're asking?
Yeah.
So I would have to use this formula, right?
Mm-hmm.
And you want me to do this formula right now?
I just want to finish.
You want to see it done? Okay. So I feel like this is not a good. I could do this, all right, and off on the side, but we don't. I don't.
Okay, just definitely later.
Okay. So I promise you. Again, we can do standard deviation by hand. I can explain why this formula works for the standard deviation. The important thing, though, isn't that this is the formula. I mean, this is important, but for you guys, what I want you to know, why do we bother calculating the standard deviation? What does it tell us? This is the important thing, okay? And I talked about this last time, but what does the standard deviation tell us? Why do we bother calculating the standard deviation? Why? Okay? Who wants to answer this question? Okay, that's the definition. The standard deviation is the square root of the variance, but why even bother calculating it in the first place? Why do we want the square root of the variance? Huh? Okay, and we just covered this in our homework, right? Homework problem 5. It tells us the spread, right? It tells us the spread, right? We have 3 ways to calculate spread. We have the range, we have the IQR, and we have the standard deviation. They are 3 different ways to calculate spread. And so the standard deviation tells us the spread. That's the important thing, okay? So that way, if you see another set of numbers, all right, let me just demonstrate this, okay? Okay, so 3 ways to calculate spread. Okay, we have the range, IQR, and the standard deviation. This was all emphasized in problem 5 of your homework. Okay, and so we looked at 2 sets of numbers. One set, I didn't even give you the numbers, but I just said which one has more spread. And based on looking at these 3 values, you can answer that question. Even if you only had 1 or 2 of them, you can kind of get a gist of the answer. So these are all just different ways to measure spread, right? It's kind of like, if you apply to live in an apartment, they're trying to get a measure of how good of a tenant you are, and so they do a few things, right? They might do a background check, and what do they check? They check your credit score. They check if you have any convictions or things like that. These are all just different ways to kind of get an idea of, is this someone I want living in our apartment? Okay. Now each of those emphasize different things, right? The credit score tells you how financially, quote, trustworthy you might be. The background might say, are you going to do any crimes or things like that, right? So again, the spread, they're all those things that the apartment complex does when you apply. They're just trying to get an idea of how good of a tenant will you be. These 3 things are just different ways to calculate the spread. The spread tells us how close together our numbers are, how far apart our numbers are. That's the idea. So let me just demonstrate, okay? So imagine these are scores here. Let's say we go to another classroom and the scores are 80, 81, 82, 86, 88, and 90. Which classroom has the larger standard deviation in test scores? So this is class 1 and class 2. Larger standard deviation. Okay, so let's ask, what is the the standard deviation of class 2? Is that going to be bigger or smaller than 26? And how do we know that? Everybody's test score is very consistent in the 80s, right? And so we can ask, what is standard deviation .s of G1 through G6? Okay, and I hit enter. Standard deviation is 4. Okay, now let's say I changed this person's score. No, it wasn't 80, but 8. What's going to happen to the standard deviation? It's going to go larger, right? Because the spread is now much bigger. And so now with the score of 8, the standard deviation is now 31. Okay, so it gets a lot bigger. And we can try different numbers, and we can see how the standard deviation is affected. Okay, so we see that. So when you change one of these numbers, that it affects how the spread is calculated. Okay, so the standard deviation is one way to measure spread. Is that okay? Mm-hmm. So I'm not so worried about you calculating the standard deviation by hand, but because normally when we want to calculate standard deviation, we just ask the computer, do it for me, rather than trying to use this formula and maybe making a mistake somewhere along the way. We just say, hey, computer, you're good at this stuff. Find the standard deviation for me, okay? And it says, oh, standard deviation 4.08, standard deviation 26.394, okay? And now the important thing is not, computer, how did you get this number? We don't care. The important thing is, okay, now that I know this, what do I do with this number? This says, oh, the numbers over here are a lot more close together. The numbers over here are more spread out. That's the important part. Do we care how the computer got this? We don't really care, okay? It's this formula, if you're curious. But that's not the important part to me. The important part is, what do we do with this, okay? What do we do with this? All right. Is that okay? So today's topic, we're going to get into correlation. Have you guys heard of this word before? A long time ago. So correlation is something, is a word that kind of crossed over from this very specific statistical meaning into something that we might hear in our day-to-day lives, okay? Not very often, but it's something that kind of pops up every now and then in topical conversations. The thing is the meaning it has in our day-to-day life is a little bit more loose. It gets similar ideas, but in statistics, correlation has a very specific meaning, okay? So the day-to-day meaning is something along the lines of, are two things connected, right?
Yep.
Right? And we might say things like, someone's gender is correlated with the TV shows they watch, okay? All right, so that's the day-to-day meaning, right? We say, someone's gender So if we know someone is female, we know they're probably more likely to watch certain shows and less likely to watch other shows. So less likely to watch Sports Center, more likely to watch, I don't know, whatever, okay? On the other hand, and of course this isn't true for everybody, but overall we might say things, we might be able to make generalized statements, okay? So that's the general idea of correlation. In statistics, we have a specific meaning, okay? Correlation only applies if we're asking, are two numeric variables connected, okay? Okay, so here, this is the important part, numeric variables connected. So when we go back to here, someone's gender, is gender a numeric variable? No, it's categorical. You are either male or female or neither. And so that's a categorical variable. And so we cannot apply correlation in the statistical sense to this question. But we can ask things like, is the day's temperature that's a numeric value, right? Is the day's temperature correlated with the amount of ice cream sold? Okay, ice cream sold measured in dollars. Okay, and is that correlated?
Yes.
Yes. Hot days, high temperature, so high values of temperature will be correlated with high values of ice cream sales, right? So if you run a little stand, if it's 100 degrees outside, maybe your sales, maybe you sell $160 in ice cream. Who knows, okay? Let's see, imagine you're working a little ice cream cart on Santa Monica Pier, okay? On the other hand, on a 40-degree day, how much do you think you'll sell in ice cream? Measured in dollars, okay?
20.
Yeah, maybe $20, right? So here we have two numeric variables. The temperature is numeric. The amount of ice cream sold, how many dollars worth of ice cream you sold, is also numeric, okay? So then we say, so in general, days with high temperature will have high sales values. Days with low temperature will have low sales values. Does this make sense? Okay? And so, in this sense, we can say correlation exists because we've got two numeric variables. All right, so I'm going to ask you a question. Can we calculate correlation? And does everyone have this down? I'm going to go to the next slide. Not yet, okay. Is that okay? Moved on. All right. So can we calculate correlation for? Is there a problem?
No, it's just like you just took.
I can go back.
No, it's just funny.
Oops, that's not the one I want. All right, you guys keep writing. Anyone still writing? No. Okay. Okay. So, can we calculate correlation in the statistical sense for okay. Someone's IQ score and their. All right, don't shout out your answers, okay? Someone's political party and whether they voted for Obama in the last election. Someone's gender and someone's So I'll let you guys write these down and then think, can we calculate or find a correlation, calculate a value of correlation for these things? And remember, in the statistical sense, we can find correlation if we're trying to look for a relationship between two numeric variables. me see if that. Okay. What do we think? Okay, so first one, someone's IQ score and their weight. Can we calculate correlation for that?
Yes.
And the answer is yes. Okay. Do you think there will be much correlation here?
No.
Okay. Yes, we can calculate a value. We can find a value. But we probably won't see a strong relationship, right? We probably won't see a strong relationship here. Okay. What about someone's political party and whether they voted for Obama in the last election? No. Okay. No correlation in the statistical sense. But is there a relationship between these two things? Yes, there is a relationship, definite relationship, but we cannot talk about it in terms of correlation, okay? But there is a relationship, okay? So if somebody is a Democrat, they probably voted for Obama. If someone is a Republican, they are less likely to have voted for Obama, okay? But of course, not everybody who is Democrat voted for Obama. Not everybody who is Republican voted against him. But is there a relationship? There's definitely, we're going to see some kind of trend, but we can't talk about it in correlation in the statistical sense, okay? But in the general day-to-day sense, could someone say there's a correlation between political party and whether they voted for Obama? Yeah, in the day-to-day sense, that's fine. Statistical sense, no. Okay? What about someone's gender and their weight? No. Okay? Again, not in the statistical sense. So no correlation here. But is there a relationship between gender and weight? Yes, in general, men weigh more than women. In general. Okay? On average, I should say. Okay? No correlation, but a relationship. Okay? In general, men weigh more than women. Okay? Of course, any individual may not necessarily fit this general trend, but overall, as a whole, if we look at all people, this is what we'll see. Someone's height and their weight.
Yes.
Yes. Okay? And what kind of relationship will we see? Yeah, so in general, tall people will what? Weigh more. Short people, in general, again, in general, short people weigh less. Not necessarily so, but in general, this is all about in general, defining general trends. When we talk about individuals, any individual may stand out and be different, but we're talking about general trends. And when we talk about correlation, we're talking about general trends between two numeric variables. Okay. So there is a number called R, and this is, or the correlation coefficient. We just call it correlation, okay? But to summarize, the relationship between two numeric variables, we use the value r. Okay, that's a lowercase r. We use the value r, and this stands, and the name is correlation, and the full name is correlation coefficient. But no one, no, I wouldn't say no one, but we don't generally use the full name, okay? We generally just say the correlation between this variable and this variable is some value here, okay? Oh, we use, I'm sorry. Correlation, we use, sorry.
So when you say the lowercase r, that means that it's correlation.
Yes, okay?
They don't say R, they'll use that R.
Right. Correlation coefficient is the full name. Okay. This, again, this is just a summary to describe the relationship between two numeric variables. We have values like the mean to summarize what? What does the mean summarize? Okay, and the average, okay, or what does the average summarize? Why, huh? It's central tendency, right? Average, the mean, the median, these talk about what values are around the center of our data set. The standard deviation summarizes what? The spread. And the correlation summarizes the relationship, okay? Are we getting this? No? All right, so that should be in your notes, but okay, so the average, so the mean and the median, they summarize central tendency, where the center of our data is. The standard deviation summarizes spread. The correlation summarizes the relationship. Okay? It should be. Should be in your notes. Can I go on, or are we still?
Yes, go on.
Okay. Are there questions up there? All right. We're just trying to summarize an aspect of the data with a single number. That's all, okay? You know, kind of like, I'm in counting, you guys have different pay grades, right? And so when somebody, you know, if somebody just says, oh, I'm this pay grade, it gives you a general idea of what their job must be like or something. Not what they do on a day-to-day basis, but you get, oh, okay, you are at this pay grade, so it must mean you have this much responsibility or whatever, right? It doesn't tell you everything, just like these summaries just give you a little glimpse of the detail, and it kind of sums up something, right? If you're applying for a job and you say, oh, you know, what exactly does this job entail? And somebody might, if they're feeling like a jerk, they can just say, oh, well, it's pay grade this, and not really telling you details about it, but it'll say, oh, okay, well, then that's that, or something, right? Sometimes, you know, especially in military, they talk about their levels and ranks and things, as if that summarizes their entire military career. Okay, anyway, so summarize the relationship between two variables. We have R, just summarizes that. Okay, so here's the thing about R. R has no units. This makes it very convenient. Okay. So when we talk about the average income of the people in the diner, there's units there. Okay, the average income is $60,000. Okay, because the units make a difference. If we said the average is $60,000 versus 60,000, rupees, we're talking about a different story. Okay, 60,000 Japanese yen. Okay, different things. So the units matter when we're talking about average. Okay, if I say, oh, so and so's height is 150, you're like 150 what? Okay, 150 centimeters, 150 inches, 150 what, right? So the units matter there. So mean, median, range, those things have units. R, no units. Okay. R is always between -1 and +1. You will never have correlation bigger than 1. You will never have correlation more negative than -1. Okay. Okay. If R is positive, it means the relationship is quote-unquote positive, and I'll explain what this means. And if R is negative, the relationship is negative. And if R is close to 0, the relationship is weak. And if R is close to 1 or -1, the relationship is strong. Okay. This section, all of these notes here, these are very, very important. Okay? You must know and understand this about R. Okay? So, all of this, you need to really learn or memorize everything in this red box, okay? And we're going to go through examples today to emphasize all of these aspects about R. Okay, so but this is I'm sorry, one more important thing I should add. Okay, one more, +1. Okay. These interpretations only work, okay? Work only for linear relationships. Okay, and I will define what each of these things mean, and we will go into it in more detail. But everything in this red box, very important. You need to know all of this stuff about R. And I promise it's not so bad. Okay, but I present all of this all at once up front, so you know all of it together in your notes. and know that this is important, and then we'll break it down one by one. It'll all make sense. Okay? Maybe not the first time around. Okay? Maybe I'm recording what I'm writing and what I'm saying into a video, and I'll post it on YouTube. You guys can review this section on your own time, just to make sure we understand. Okay, so let's pretend to have some data here. So let's think of two variables that might have some kind of relationship. Two numeric variables that might have a relationship. Can you guys think of anything? Height and weight. Okay, so let's say we have different person, and so let's say we ask Adam. Adam, how tall are you? Adam says, I am 70 inches tall. I weigh 165 pounds. You don't have to. You can write this, okay? But you don't have to, okay? Well, you go to the next person. Let's say there's a person, Betty. Betty says, I am 65 inches tall, and I weigh 130 pounds. And who's next? I'm going with my ABC theme here. Okay, Carl, let's say, is 5'8", so he's 68 inches tall, and let's say he weighs let's put him at 180. Okay, and Debbie, she is 60 inches tall and weighs 110. I don't know, I'm just making up numbers here, okay? And we could imagine gathering data from a whole bunch of different people, asking them, how tall are you? How much do you weigh? Okay? All right, and so let's say Ed is just trying to make up some more numbers here. 72 and weighs 185. And I don't know. Francis is 61 inches and weighs 140. Okay. I don't know. All right? I'm just making this up. We are going to make a scatter plot. Okay? Are you guys familiar with a scatter plot?
Yes.
Okay? What? Okay. So a scatter plot, I'm gonna make a I want to keep this here, but a scatter plot, you have an x and y axis, and then whatever points you have, you graph coordinate pairs, right? And you put the dot wherever they are. Things like that, okay? So this is a scatter plot. Okay? So just an example scatter plot. We're going to make the scatter plot using our data that I've typed into Excel. Is that okay? So to do this, I'm going to highlight the data that I've typed in, and I'm going to say, Excel, I want to insert a chart, okay? And this is the chart that I want. Insert a scatter, okay? So I'm going to just click down, and I want this one right here. And so this is what we have, okay? So I've got height and weight, and this is how it goes. And you can make edits and things like that. More options. We can change the minimum here. Maybe. Okay. So here's the scatter plot, and so starting at 58, it goes up to 74, and we've graphed these different people, right? So who's this person? This is Debbie, right? 60 pounds, weighing 110, okay? Who is this person? This is Adam, okay? So can we see this? Everyone's okay with the scatter plot? Okay. So just looking at this, does it seem like there's a relationship between height and weight? And we would say yes. It seems like, looking at the 6 people, the taller someone is, the more they weigh, okay? But, you know, you compare two people. Adam is 70 inches, which makes him taller than Carl, but he weighs less than Carl, right? Carl is 68, he weighs 180. Adam is 70, and he weighs 165, okay? So, you know, any two individual points may not necessarily be in this relationship, but overall, there is a relationship where higher values of one variable, height, is associated with higher values of weight, okay? So this is what we call a positive relationship, okay? So let me see where I can enter this. I'm going to just put it over here. So this is, so it looks kind of like this, not necessarily, but this is a positive relationship. All right, and I'm going to write that here, okay? So positive relationship means large values of one variable. So large values of x are associated with large values of y. Small values of x, this is what positive relationship means. Small x goes with what? Small y, right? That's what a positive relationship means. Big X goes with big Y, small x goes with small y. And x is just a generic placeholder for whatever variable is here, right? Okay? So going to my scatter plot, what is my x variable? What's going across my x variable, x-axis? The height. Height is x, and y is weight, okay? So in that scatter plot, x is height, and y is weight. And we see, in general, people with big X, meaning they are tall, big weight, way more. Small x, so Debbie, she is 60 inches tall, small x, small weight, 110. The tallest person, Ed, 6 feet tall, 72, high weight, 185, okay? I mean, I just made up these numbers, but this is what we have, okay? So our correlation, the value R, should be equal to what? Should it be positive or negative?
Positive.
It will be positive, okay? Because I said this is a positive relationship, and in the other slide I said positive relationship means R is going to be positive, okay? All right, so to calculate correlation in Excel, you write equals correl, and then you put in the range of the x variable. So I'm going to put in, so what is the range of my x variable? B2 to B7. You guys can see that?
Yeah.
Okay, so we're going to put in the range of our x variable. So I'm going to put B2 colon B7. So this is the x range. Range not being the statistical range, but in Excel they call it a range also, or array. Maybe I'll use that word, array. And I'm going to put in over here, comma, the y array. So what is the y array? C2 through C7, right? So I'm going to do C2 colon C7. And this will produce the correlation value. Is this okay? All right, so wait a minute. Okay, I'll go back. Does this make sense? Okay. So I'm going to. Are you confused or lost?
What's that mean, array?
What does
What?
what array?
Mm-hmm.
So it just means the kind of this from here to here. When you have select multiple boxes in Excel, it's called an array. Okay. When you select one box, it's called a cell. When you select multiple boxes, it's called an array. That's all. All right. So you can have array. You know, this is an array. This is an array. These are all arrays. Okay. You select one, it's called a cell. Okay. That's all. So here I'm going to type in equals, and I'm going to do correl for correlation, and see, it even asks, it says give me array 1, and you highlight what it is, B2 B7, or you can type it in yourself, C2 colon C7. Okay, and it highlights it on the screen. All right, so what do we think? Do we think the correlation is strong or weak? We haven't really talked about that, but let's see what value we get. 0.8848. That's the correlation between height and weight. Okay? So according to our data, we have a pretty strong correlation, fairly strong relationship between height and weight. It's positive, and we're getting 0.8848. Is that okay? So we calculate it, and we get R is equal to 0.8848. Remember, from the previous slide, let's go back one slide. R is positive, means the relationship is positive, which is what we see. And if R is close to 1, which it kind of is, it means the relationship is strong. All right? So I'm going to do another example where maybe the relationship is weaker, and we will see how that works. Okay? Is that okay? All right, let's plug in. Let's say we asked each person not just their height and their weight, but let's say we asked them, what is your IQ score? Okay? Or yeah, we could do age. Sure. It doesn't matter. Okay? All right, so Adam, he is 70 inches tall, but let's say he's 28 years old. And let's say Betty is 53. And let's say Carl is, I don't know, 42. And Debbie is 40. And Ed is 34. And Francis is 36. Okay? It doesn't, right? It doesn't matter. Okay? I'm just plugging these in. So let's create a scatter plot here. Okay? I'm going to just move this one over here. I want to make a scatter plot between height and weight. Okay? And so it's gonna get wait, can I do this? Let's see. We want to insert a scatter plot. This is gonna get angry here. You know what? I'm sorry. I think I have to put this down. I think I have to put them next to each other. So I'm going to just copy this over here, okay? So basically I'm making the same table, except we're taking the height information and we're plotting it against the age information. Is that okay? And we're going to make a scatter plot here. I should probably make its own page. So we're going to insert a scatter plot. I'm going to highlight height and age, and we're going to do a scatter plot here. Okay? And again, I'm going to edit the axes here and change the vertical axis so maybe it starts at 20. Because it likes to start at 0, but let's go to 20. And maybe even 25. That looks good. Okay.
What's the age?
So, I don't know why it. You just get rid of the chart title. Okay, so this is looking. The x-axis is height, and the vertical axis is age. Does it seem like there is a relationship between someone's height and their age? Can we say anything in general, like people with high height have high age or low age? People with low height have high age or low age? No, it doesn't seem like there's any kind of relationship like that, right? So can we calculate R? Can we calculate correlation for this? Is it possible? Yes. Okay, we have two numeric variables, right? Height and age. So we can calculate correlation, but what do you think that R is going to be? Negative, maybe negative, probably it looks, if we were forced to say big numbers go with big, high or low age, it's very hard to say, but if we were forced to make a choice, we would say negative, but then would we say that relationship is strong or weak? Weak. So what kind of value do you think you'll see for R? Probably not exactly 0, but we'll see something negative, but small, right? So let's do this, okay? So what would I enter here? I would say equals correl for correlation, parentheses, and where would my first array go? B12 colon B17, very good. And then C12 to C17. Okay, and you can see the boxes form around it. Does this look good for everyone? Okay, and we're going to hit enter. And what do we get? Negative 0.35. Okay, now this might feel like it's bigger than you expected, right? More negative than you expected. Maybe you're expecting like negative 0.1 or something. Okay, well, when you have just a few data points, it's easy for things to seem bigger than they are, okay? But as the number of data points increase and there's more and more no pattern, you're going to get values closer to something negative here, okay? So here I have R equal to negative 0.35. Is that okay with everyone? Okay, so let's make a new slide. I'm going to just punch this in here. Okay, and here, so we have R equal to negative 0.35 or something like that. Yeah, 35378. Okay, so overall negative trend, but not very strong. Is that okay? Okay, so I'm going to do, I'm going to just do something a little bit quickly in some code here, and don't worry about it. But just give me a second here. Yes.
So it's not very strong. For it to be strong, it needs to be like maybe 0.1 or something. He says not very strong.
Okay, so we'll get into what not very strong and all of that stuff means, but it truly it's a little bit subjective. Okay, so let me just I'm sorry? The sign-in sheet? The sign-out sheet. Okay, sure. Let's let me get that started, I guess. Give me a second. All right, so I'll pass the sign-out sheets around. Let me. All right, so I'm going to. So I just generated a bunch of random data here, and we're going to insert a scatter plot here, and this is what we get. This is with 100 data points. Okay, and so let's say let me just set the minimum to be like 55, and the maximum to be, we'll say 150. Okay, and then as for the vertical axis, we'll set the minimum to be, we'll say 48. Or, no, let's just do 50. 50 to 70, 75. Okay, so this is with 100 data points. Okay, and we're going to, this is going to be height, IQ, IQ versus height. Okay, so this is as if we asked 100 different people, what is your IQ score? And we asked, how tall are you? Okay. And does it seem like there's some kind of trend between how tall someone is and their IQ score? Oh, not really. Okay. This one person will probably make a big difference here. Okay. This is someone who is short with a low IQ. Okay. And we might want to remove this person. Let's see, 0.62. We might want to do a calculation with and without. What was that?
30.54.
So okay, don't worry about it. Okay, we're gonna do. So what do you think will be the correlation if I calculate the correlation here? So I'm gonna say correl, and I want to do from A2 through A1. I think A101. Yeah, A101. Okay. So it equals correl what? A2 through A101, and we're gonna go to B2 colon B101, right? And I hit enter, and I get 0.016971. Okay, so it's very small, right? That's kind of like saying there's pretty much no correlation at all. Okay, you're almost never going to get exactly a correlation at 0, because that means your data have to be aligned in such a way that all the numbers cancel out in this fashion. Okay. We're not going to, but you're getting something very close to 0. And so what we see here is pretty much no correlation at all, right? Oops, that's not what I want. So if I copy this and put it over here, IQ versus height, my correlation turned out to be 0.169? 1697, okay? So pretty much 0.02 if I round off to 2 decimal places. So this is very, very weak, okay? Or, you know what, practically, on a practical basis, practically speaking, no correlation at all. Okay? We're saying Is someone's IQ score related to their height? No, okay? IQ score is not related to height, according to this data. Now, if we measured height and income, would we see a relationship? We would actually see a very weak but positive relationship, and there have been studies that have shown, for people are terrible, and that for unexplained reasons, taller people get paid more than shorter people. Okay, it's not fair, but that there is a general trend. Okay. And I mean, especially if you factor in professional athletes, if they get factored in, almost all professional athletes are very tall. Everybody sign out? Okay. No? Sign out, please. Okay, so we have that. Okay, so we have this. Is this okay with everyone? Okay. Did anyone see the movie Moneyball?
Yeah.
Okay. Do you guys, what happened in Moneyball?
He was trying to get people that actually hit to first base, not necessarily.
Yeah, so they had this stats guy, right?
Yeah.
And he worked with the general manager, basically the head coach of the baseball team. They're called the manager, and the stats guy was trying to say, you know what, the traditional scouting methods were things like we're going to look at the swing form and all of this and all of these kind of subjective measurements, and the stats guy was like, no, let's just look at this thing called on-base percentage, which means when they're up to bat, whether they get walked, which means the pitcher threw poorly, and so the guy gets to advance to first base because of pretty much the pitcher's fault, or whether the guy actually hit the ball or whatever. If he manages to get to first base, it's called an on-base, and that's a good thing. And so I don't know if you guys are interested in this kind of stuff. I realize maybe I'm talking to the wrong audience, but okay, huh? Maybe not. All right, huh? So we can look at runs scored, okay, and this is kind of a measure of how many points did a baseball team score, okay? And so what this line says is that the Arizona Diamondbacks, if you guys care, they scored 731 points over the course of the 2011 season, okay? So there's like 162 games in a season, and they scored a total of 731 points, okay? And so basically successful teams, so like the Boston Red Sox, they scored a lot, 875. Poor teams that year, they scored, like Pittsburgh, only scored, or San Diego Padres only scored 500, so Seattle did poorly, okay? So anyway, we could look at the runs scored, okay? And we can look at things like this. So batting average, are you guys familiar with what a batting average is? Okay, it's kind of a measure of how often the person hits the ball when they're at bat, okay? So we can create correlation between runs scored and batting average, okay? What kind of value do you think we'll see for the correlation between batting average and the total number of runs scored? So you think higher batting average goes with more runs scored, or higher batting average goes with lower runs scored? Yeah, so we're going to see a positive number, right? And do you think the relationship is strong or weak? Okay, so we're going to do runs and batting average. Okay, so I'm going to do correlation between runs, so C2 through C710, okay? And we're going to do the same thing, but for batting average, okay? And I get a correlation of 0.768. That's pretty good, okay? But the character in Moneyball, okay, he was saying a better thing is on-base percentage, okay? So let's see what's the correlation between runs and on-base percentage, okay? And we can ask, okay, well, Excel, give me the correlation between runs, so how many points the team scores, and on-base percentage. Let's see. And what do you think the correlation there is going to be? It's stronger, 0.89, okay? So we have an improvement, and I would say this is a significant improvement between the traditional measure of batting average. On-base percentage has a stronger correlation with points scored, okay? And then there's something called slugging and on-base plus slugging. So slugging kind of talks about how strong a batter hits. So like Barry Bonds had a very high slugging percentage. Maybe because he used drugs, we don't know, okay? So if we look at slugging, which is just another number, okay, all we're doing, okay, we get a number like 0.92, okay? So even better. And then if you combine on-base percentage plus slugging, runs and on-base plus slugging, which is called OPS, we can ask the correlation there. And we'll get okay, 0.957, okay? And so this is very high. That's about as close as you can get to 1 in real data settings, okay? Because in real data settings, you almost never get close to 1, and you are seeing something very high here, okay? And so, you know, Moneyball, the movie is, it's a good movie. It's you know, they kind of show the emotional side of the manager Billy Bean and things like that, but behind the statistics behind it was actually very real, and there is a very strong relationship between these newer ways to measure baseball statistics versus the classical method, such as at bats. Okay, and so here's the statistics behind that. So I hope that was kind of neat. Okay. I guess I should just cover maybe. So we talked about a positive relationship. What do you think a negative relationship means? So negative relationship what does a negative relationship mean? Not no relationship. It means large values of x go with what? No, in a negative relationship, large values of x go with small values of y. And small values of x go with large values of y. Can you think of anything that will have a negative relationship? Two variables that will have a negative relationship. What's that? Temperature and... No, I wouldn't say days of the week. So remember, we need to have two numeric variables, right? So days of the week is not a numeric variable. It's categorical. It's Sunday, Monday, Tuesday, Wednesday, or something like that. So we need two numeric variables. So maybe temperature and earmuffs sold, okay? What's that? Or sweaters sold. We can do that, okay? So temperature versus sweaters sold, right? Measured, you know, temperature in degrees Fahrenheit. So on a 100-degree Fahrenheit day, how many sweaters do you think get sold at Macy's. Yeah, I don't know. Maybe they're like, maybe $25 worth of sweaters or something, right? They're on sale. It's like, oh, we got to get rid of this stuff that nobody's going to buy. Okay, maybe. But in general, overall, if we're looking at people aren't buying sweaters on a 100-degree day, okay? On the other hand, let's say it's 40 degrees outside. People are like, oh, it's time to get that sweater that I wanted or whatever, right? So we're going to see, large values here, maybe $200 or whatever, small store. So anyway, that's a negative relationship. Large values of x go with small values of y. Small values of x go with large values of y. Okay, or maybe think of your car value. Car value and its age. Okay, let's say you buy the car at $25,000, 0 years old. After 1 year, it goes down, right? I don't know, 22,000. I have no idea. All right, I'm just making up numbers. After another year, it goes down even further, and it's depressing, right? And then so after 10 years, your car is worth like $9,000 or something like that, right? So we see large values of age go with low values for the car worth. Small values of age go with large values of the worth, okay? So this would be a negative relationship. Is that okay?
Core value is X.
It doesn't matter, okay? You just assign one to X and one to Y. It does matter next week when we talk about linear regression, okay? But right now, or not next week, in 2 weeks, okay? When we talk about X and Y or X and Y, it does matter for the next lesson. But right now, we just want to know, is there a relationship between the two variables? And over here we see, low age, so small age goes with large value. High age goes with low value. Okay? So that's a negative relationship. Is that okay with everybody? Okay? And we talked about strong and weak relationships. We saw the IQ and the height, no real relationship, whereas something else we had a very strong relationship. Okay? Such as, so I could, I can create a plot between runs and on-base percentage and runs and batting average just so you can see the difference between 0.768 and 0.957. Okay, so I'm going to just create two things here. Okay, so I'm going to do runs scored and batting average. So I'll make a plot here, and you can see the difference between what it means to be 0.957 and 0.768 with lots of data points. Let me adjust these axes. So I want something like 420, and over here I want maybe like 0.2. Okay, so we can see this is a correlation of 0.776. And then let's do the other one. Just give me a second to pretty much create these plots here. Okay, so you guys can see over here there's very strong, almost like a very straight line, right? This is 0.97. R is equal to 0. What was the calculation? I forget already. 0.958 and versus 0.768. Yeah, 0.958 and 0.768. So here this is very much like a straight line. Okay, and this is pretty straight, but a little bit of scatter, right? So you can see the difference between r equal to 0.768 and r equal to 9.956 when you've got lots of data points. Okay. All right, I know we got 20 minutes left. Huh? What's that? That's party. So I have to. There's stuff I still want to cover here. Okay, and this is the shortcomings of correlation in R. Okay, so these interpretations saying it's strong when it's close to 1, it's weak when it's close to 0, it's positive and it's negative. These only work for linear relationships. So we should always, when you have data, always make a scatter plot and say, does it kind of make sense to use a straight line? Okay, so this is one rule. So always make a scatter plot and ask, does it make sense to try to fit a straight line? Okay, because our interpretations for R, and what I mean by that is that red box that I said very important. Okay, our interpretations for R only make sense if a straight line fits our data. Okay, and we can have all sorts of situations where a straight line does not make sense. So I'm going to show you 4 data sets. Okay, do you guys all have this written down? Okay, I'll give you guys a moment to write that down.
When you say straight line, what are you referring to?
What am I referring to? So let me let everybody write this down first, and then and I'll talk about what it means to have a straight line. Does everyone have it down now? Yeah. Okay. So when we look at our picture, it seems like a straight line, like we can fit a straight line in here, and it kind of makes sense, right? And we can fit a straight line. We can definitely fit a straight line here, and that kind of makes sense. Okay. I will show you some examples where it doesn't make sense to fit a straight line. Okay. So let me pull up some data here. I'm so glad we got the computer projector, because it would have been, I would have had to try to draw these things by hand, and it would have been a bit of a disaster here. Okay, so I'm going to do some correlation calculations here, okay? So I have, I'm going to just highlight these, so don't worry about this, but this is one variable and another variable, and then this is another 2. I've got 4 different data sets. Each of them have 11 data points in them, okay? And we're going to calculate the correlation for each of these data sets. Okay, so if I do correlation of A2 to A12 and B2 to B12, the correlation value is 0.816. Okay, I'm going to do the correlation right here also. Correlation for B2 to B12, C2 to C12 and D2 to D12, okay? And the correlation there is almost the same. And over here, and these are just shortcuts, but I can calculate the correlation for each of these pairs here. And it's being covered by, let me just move it up top here, okay? And so you can see all of the correlation values are around 0.816. Okay, so it seems like, oh, maybe the correlation is pretty good for all of these things, okay? And looking at the numbers, you would have no idea that correlation only makes sense for one of these data sets. For the other ones, the correlation doesn't make sense, okay? And so I'm going to draw you this graph. We're going to insert a scatter plot. Okay, and you look at this data, and yeah, does it make sense to try to fit a straight line here? Huh? Yeah, kind of, okay? Kind of, right? I mean, there's scatter. Yes, there's scatter, but overall, it makes sense. It's kind of like it's not a perfect straight line, no, but does a straight line kind of generalize the thing to say larger x goes with larger y? Yeah, that works, okay? So this is the red one, the A, all right? I'm going to do this one with the B. So let me show you. Let me put this into a new thing, and I'm going to put all of these over here. And all of these notes I'm going to publish online, okay? So you guys can reference them also. Let's do one for this. We're going to do a scatter plot here. Look at this. Okay? So here, correlation is still 0.816. Okay? Does it look like a straight line here, though? No, it definitely looks like there's a curve, right? Okay? But correlation, that R value, has no idea. It doesn't know that. It just says, okay, oops, I didn't want to do that. I'm trying to fit a straight line, and if I had to do that, what's the relationship? It just kind of describes the relationship, and it says, oh yeah, overall there's positive, and it looks pretty strong, so I'm going to say 0.816. Okay, but it's not taking into account that there is a curve, because R isn't smart enough to do that. You have to look at the scatter plot yourself and just say, hey, does this make sense here? Okay, I'm going to draw another one here. We're going to insert a scatter plot. Okay, what's going on here? Okay, it looks like a straight line, but there's one right here, right? So if this line was in here, what would our correlation be? It would be 1.0, right? It would be 1.0 because these would all be in a perfect straight line because this one is in here. But this one sticks out, okay? And this one sticks out enough that the overall correlation drops down to 0.816 like all of the other ones. So I'm guessing what happened here is somebody typed in the number wrong, okay? Right? If you see something like this, if you look at a scatter plot like this and you're like, oh, every single year it goes like this, and then 1 year's up here and then next year it goes back in trend, you'd have to be like, something either very strange happened here, which doesn't make sense at all, or maybe somebody typed it in wrong. You want to look into what happened here. You don't want to just say, oh, here's my data, my correlation is 0.816 just like everything else, la-di-da-di-da, okay? You're gonna miss something here, okay? And let's look at this last one here. Okay, what's going on here? So right here, yeah. So this is, remember, we're trying to see if there's a relationship between X and Y, okay? And this would be somewhat like you're going to ask, let's say you want to know, is there a relationship between age and height, okay? and you say, okay, I want to know if kids who get older get taller or something like that, okay? And this is a silly example because we already know the answer. But to answer your question, you only survey 8-year-olds. And you say, how tall are you? And all of your data is just 8-year-olds, okay? If all of your data just comes from 8-year-olds, are you going to be able to establish a relationship between age and height? No, because you have no values other than 8, and that's what we have going on here. And so it's like, oh, I surveyed a whole bunch of 8-year-olds, and they have different heights or different values of this, and then I surveyed one person who was 19, and he's up here, okay? And so because of that one 19-year-old or whatever, now you're saying, oh, well, the 19-year-old was tall, and all the 8-year-olds were short, so this is my relationship. That's not a good plan, right? If you want to know what relationship there is between age and height, you want to get a bunch of different ages, a bunch of different heights, and form a relationship like this, okay? So let me just kind of annotate this, and you don't have to write this down. It's going to be saved up online. So this one, correlation makes sense. Okay, here R does not work. Why? It is clearly not a straight line. Okay, there's a clear curved relationship, right? What about over here? Okay, here it seems there is one data point that is odd. Okay, all of the other data points, all other data seem to fit a straight line perfectly. Okay, we should investigate this odd point and not just say, okay, so anytime sometimes you make scatter plots and then you see strange things like this, okay? And this is nearly all of our data exist only when x equals 8, okay? So we should not be able to calculate correlation at all. We should not calculate correlation. Okay? But we do have one data point out at 19. And 19, so this creates the illusion that there is a positive relationship. Okay. Does that make sense to everybody? Okay, so I'm still writing your homework assignment. Again, I'll have it posted by tomorrow morning, the final version of your homework assignment. Would you guys be okay with using Excel to calculate the correlation coefficient? Okay, just in the way I've done. Not everyone has Excel? Okay, so do you guys have, you guys can also sign up for a Google account, Gmail account or a Google account, and you can access Google Drive, and it will work in a very similar fashion, okay? Well, I'll try to make an assignment that is fair and works for everybody, okay? So we'll see. Okay, yes, you guys can email me, of course.